Hello everyone, let's continue. So in the last video, we came up with two different definitions of states. So DS0 and PS0 were the two different states where DS0 represented the state of the non-inverting output and PS0 represented the state of the inverting output. So now let's try to look into where are these being used. For that, we need to open up the Liberty format description of the flip-flop. If you open up the flip-flop, the description looks something like this. You have the cell definition and the different cell attributes. You have the pin definition, different pin attributes, and this all remains the same as we have discussed in a couple of videos in the past. And the important part over here is this particular description. So if you look over here, the flip-flop is being described over here. The P007 and P008 are the different states that we were talking about in the past. So it could be a different name. In the previous case it was DS0, over here it is P007. So the location of these characters represents the state. So for example, P007 has been located before the comma, and that represents the state of your non-inverting output. P008 has been located after the comma, and that represents the state of your inverting output. So that's how you define your different states, and it could be any name. It could be name called as state 1, state 2, or something like that. So that doesn't matter. The location of the location of those characters defines what it represents. The flip-flop group attributes like the next underscore state, which is D, the clock down is clock, capital clock, these are all remains the same that we have seen in the past video. The clear is the R bar, preset is S bar, clear underscore preset underscore var, I have kept it as L, and for the var 2 also I have kept it as L. So the definitions of all of them remains the same that we have discovered in the past. The important thing to note over here is the definition of the Q. So in this case, in the previous cases, wherever we had to, in the combinational cases, wherever we had to define the function, we used to give a combinational, we used to represent it by a combinational function over here, and that's or a boolean function over here. In this case, in specifically the case of a flip-flop and latches, the function only accepts states, and that's where it uses it. So P007, when I say the pin output or the pin is Q, the direction is output, the function is P007, that automatically represents that goes over here. It checks out the definition of P007. It means to us that P007 is a state, is a state which is represented by next underscore state on the application of positive edge trigger of the clock. That's how it is being used. So P007 is being used over here. Similarly for P008 is if there was a pin called as Qn on the flip-flop, the definition of the pin Qn, since it's an output pin, for all the output pins of sequential elements like the case that you see over here, the function only accepts the logic states, or it only accepts the states of the inverting and the non-inverting output. In this case, the pin Qn, the function is P008, and P008 defines the state of the inverting output, which is being given by this definition. Again, it represents the meaning or the definition of function equal to P008 remains the same. It tells to us that whenever it receives a positive edge trigger of the clock, the next underscore state becomes D. So P007 becomes the next state, and P008 becomes the invert of P007, and that's what is being mentioned over here. And that's how you describe a flip-flop. And this is the way any STA tool represents or interprets a flip-flop definition inside a timing mode, inside a Liberty format, inside a lib file. Okay, so that was about the flip-flop. Similarly, if you look into the latch definition, things remains exactly the same. There are few changes over here. So for example, latch can also be defined using a latch group and the state table group. Now if you open up the latch description, it remains exactly the same as we saw for the flip-flop. Only FF is being replaced by latch. The clock is being replaced by enable. The next underscore state is being replaced by data underscore in, and everything else remains the same. Because in this case the enable it was a edge triggered flip-flop. In this case it's a level sensitive latch. So whenever your G is 1, your DS0 becomes data in, which is D, and your PS0 is nothing but the inverted form of the DS0. So let's say this was the latch. So whenever your G is logic 1, your D becomes the next non-inverting state, which is DS0. Your inverting state PS0 is nothing but the inverse of DS0, and rest all definitions remains the same. Now again, in order to understand where is the DS0 and PS0 are being used, we have to look into the description of the latch inside in the Liberty format. But before that, this is the table that we have in the past. This was clock. In this case it is G, it is the enable pin. Rest all definitions and everything remains the same. So for example, if G is logic 1 and this both are inactive, your DS0, which is the next state on the whenever your G is logic 1, is data underscore in, and your PS0, the state of the inverting output, is nothing but not of data in, and rest all remains the same. The clear preset var 1, the clear preset var 2, whenever both are active, they all remains the same. and that's the definition of the latch. And similarly, we have to answer the same question, where are these being used. Again, we have to look into the liberty format or of the latch description over here. This is the latch description. Everything else remains the same. Only you have instead of the data, instead of the clock, you have enable attribute over here. Instead of the next underscore state, you have data underscore in. Everything else remains the same. The function, the output function, in this case for the queue, the function is again p007, but in this case p007 represents a state which is data underscore in only on the logic level, only on the level 1 of your enable signal. Okay, that's the only difference. The rest all is the same as we have seen for your flip-flop. Okay, so that was about the different behavior of the flip-flop and the latches, and that's how you represent your flip-flops and the latches in a flip-flop or a latch group. Next is a very important thing, which is a state table group. So same flip-flop and the latches can also be defined using a state table group, which is a more compact form of representing a flip-flop and latches. Understanding the state table group will also help us to define or describe any complex sequential models like memories and so on. So that's what we are going to do. So let's try to so what we'll do is we'll stop at this point and we'll start from the state table group. So state table group needs some amount of theory. It needs some knowledge about the finite state machines. We'll talk about the finite state machine and a bit about the finite state machines and how is that being used to describe flip-flops and latches. So let's talk about the state table group from the next video. Thank you.